Hello students, welcome to BTech first year bridge course. In the last lecture, we have discussed about electrostatic energy of discrete and continuous charge distribution. Now today in this class, I will discuss some basic properties of conductors. Now first question comes to our mind, what is a conductor, right? So conductor is a material through which electrical current can conduct easily. So why it happens? It happens due to the presence of large number of free charge carriers, that are electrons. Now examples of conductors are metals such as iron, copper, gold, silver, etc. Now how a metal forms? The metal is actually available in solid form, right? Now all the atoms of metal, suppose for iron atoms are closely spaced and they are arranged in regular manner. Then they form a solid iron metal. So when they are closely spaced, due to the interaction between two nearest neighbor atoms, the valence electrons of the two nearest neighbor atoms become free and they can move in the conduction band very easily. That is why the conductivity of conductor is very high. Now in perspective of electrostatics, conductor has some important properties that we will understand today in this lecture. Okay, so let's start. First important property is electric field inside a conductor is zero. Now let's understand why it is so. You know, in a perfect conductor, there is no resistance to the movement of charges within it. Now, if electric field is not equal to 0 inside the conductor, then free charges would move inside the conductor and no static equilibrium would be possible. So, we can establish that electric field inside the conductor is 0. Okay. Now, if a conductor is placed in an external electric field, then let's understand how the electric field inside the conductor is modified. Due to the presence of external field, positive charge piles up on the right side surface of the material and negative charges pile up on the left surface of the material. These induced charges produce an electric field E1 inside the material in the opposite direction of E0. So now the movement of charge continues until E1 cancels the external electric field E0 and the resultant electric field inside the conductor is 0. Okay. So this whole process is very much instantaneous. This is very fast. Okay. Now let's discuss another important property of conductor, that is charges given to a conductor reside on its outer surface. That means charge density rho equals 0. Now to prove this, let us consider the charge density is not 0 at any point inside a conductor. So now using electrostatic Gauss's law, we can say that electric field will be non-zero inside the conductor, but we have proved that electric field is 0 inside the conductor, which implies that charge density is 0 inside the conductor. So whatever we have assumed about charge density that exists inside the conductor, that is wrong, right? Now let's understand physically. The charges in a conductor are free to move, right? and they ultimately take a position in such a way that electric field inside becomes zero. The surface is the only place where the charges can go, and they cannot leave the surface because of the existence of surface potential energy barrier. Okay, so next property is conductors form equipotential region. Now let's prove this. We know that the electric field is zero inside the conductor. Now here A and B are any two points within the conductor. Now the potential difference between these 2 points can be written by this equation. So this already has been discussed in one of my previous classes, right? As electric field is 0 inside the conductor, this integration value will be 0 and potential difference is also 0. So we get the potential at B point is same as potential at A point. Thus the potential is constant throughout the conductor, right? Now the conductor surface also forms an equipotential surface. Otherwise, charges would flow from regions of higher potential to lower potential, giving rise to current on the surface. But that does not happen in static equilibrium, right? So that is why we can say conductors form equipotential region. Next important property is the electric field just outside of a conductor is perpendicular to the surface. Now to prove this, let's consider if the electric field is not normal or perpendicular to the surface, then the electric field vector have two components, right? One is the perpendicular component and other is the parallel or tangential component along the surface of the conductor. As a result, charges will move around the surface of the conductor as they will feel some force due to the tangential component of the electric field, right? But here we have static equilibrium, so the electric field must be normal to the conductor surface, right? So we can justify this in different way also. As we know, electric field is minus of gradient of potential and conductor surface forms equipotential surface, that means potential is constant, then the gradient of any equipotential scalar surface forms a vector which is normal or perpendicular to the equipotential surface. So this is very important. So this vector is basically electric field vector. So we can tell electric field is normal to the conductor surface. Okay. Now let's calculate the electric field strength just outside a conductor. So to calculate that, let's consider a conductor surface and draw a cylindrical Gaussian pillbox and use the integral form of Gauss's law. Here delta S is the area of the flat surface of the Gaussian pillbox. Now as the electric field is perpendicular to the surface of the conductor, there will be no contribution in the flux from this curved surface of the Gaussian pillbox. Only contribution in the flux comes from the flat surface, which is delta S. Now as the electric field inside the conductor is 0, the flux will be E dot n cap delta S, which is equal to the charge enclosed by the Gaussian surface, which is sigma multiplied by delta S divided by free space permittivity epsilon naught. Sigma is here is the surface charge density, right? Now here you should note that charge is placed only on the outer surface of the conductor. Okay. Then we get the form of the electric field outside the conductor is sigma divided by free space permittivity. Then in vector form the form will be like this. Here n cap is the unit normal on the surface of the conductor. So this result is sometimes called Coulomb's theorem. Okay, so this is not Coulomb's law, this is Coulomb's theorem. Okay, the next property is charge distribution on the surface of a conductor may not be uniform. Now let's prove this. You know that conductor surface forms an equipotential surface, right? Now from Poisson's equation, we can tell that the charge density would depend on the curvature of the surface. Now why it is so? It is because when we have a scalar surface or scalar function, if we perform second order partial derivative on the function or second order derivative on the function, it will give us the curvature of the surface. That is why it indicates that the charge density depends on the curvature of the surface, because del square V gives us the magnitude of the curvature of the surface. Okay. So the surface density of charge on a conductor is greater at points where curvature of the surface is more. So here the curvature of the surface is more. So that's why greater charge density is here. Okay. Now let's understand, if there is a cavity inside a conductor, what will be the field inside that cavity? Now if a charge is given on the surface of a conductor, the charge will lie completely on the outer surface of the conductor. That already has been established, right? And then it will not produce any field inside the cavity. Now, even if the conductor is placed in an external electrostatic field, the field cannot penetrate the conductor. It is cancelled at the outer surface by the induced charges there. Now, if the cavity is empty, that means there is no charge is kept within it. Then the field within the cavity would be 0. And there would be no induced charge on the surface of the cavity. Now, why will it be happen? Let's prove that. Suppose there is a field inside the cavity and induced charges are there on the surface of the cavity. So, field line within the cavity starts at positive end, positive charge, that is plus q, and ends on the negative charge minus q on the surface of the cavity. Let us now consider a closed path C, part of which crosses the cavity along the field line and rest of which lies on the inside the conductor, where you know the electric field is 0, right? So as a result, total closed line integral E dot dl along this path C will be non-zero, because the electric field inside the cavity is non-zero but outside it is 0. So as a result, total closed line integral will be non-zero. But you know, for electrostatic field, the total closed line integral of E dot dl will be 0, because electrostatic field is conservative in nature, right? So we can say there will be no fields inside the cavity. inside this empty cavity, or there will be no induced charges on the surface of the cavity, right? Now application wise, this principle plays important role. It helps in placement of sensitive and expensive apparatus inside a grounded Faraday cage to shield out stray electric fields. Okay, so this is the important application. So you have understood different important properties of conductors from this class. Now today I am ending here. This is the last lecture of electrostatics, and from the next class we will discuss magnetostatics. Okay, thank you.